This lecture is all about common drain amplifier working at low frequency band. I'll explain the performance of common drain amplifier and will derive the expression for lower 3 dB frequency of common drain amplifier at low frequency band. I refer my earlier lecture number 9 for the development of a small signal equivalent circuit for MOSFET amplifiers and lecture number 11 for the derivation of the transfer function of voltage gain for common drain amplifier at mid frequency band. Starting with the characteristics of common drain amplifier, this is better known as source follower. Its open circuit voltage gain is slightly less than 1, close to unity. At this point, the source potential is slightly smaller than gate potential. It has very high current gain and high input and low output resistances. This is used as a buffer stage. It's a coupling device between low input to high output resistances, and there is no body effect. We assume that body and source terminals are interconnected and there is no phase reversal between input and output signals. As far as structure of common drain amplifier circuit is concerned, we are using single stage MOSFET amplifier and signal ground is achieved at the drain terminal. That's why there is no resistor connected with the drain terminal, and input voltage source and load resistors are connected by using high valued coupling capacitor CC1 and CC2. This is the device and this is the biasing resistor, this is the source resistor, and output is taken across the source resistor via coupling capacitor CC2. At low frequency band, the internal capacitor CGS and CGD, they behave as an open circuit, but high valued coupling capacitor CC1 and CC2, they don't behave as a short circuit. So at low frequency band, gain starts falling, and this is the rate 20 dB per decade. At break frequency or lower 3 dB frequency, gain falls by 3 dB and the slope of asymptote to the gain function increases by 20 dB per decade at this frequency. At low frequency band, the circuit of common drain amplifier behaves or exhibits the properties of first order high pass network of single time constant, which can be represented by a very simplified circuit where capacitor is connected in series and resistor as a shunt element. For this simplified first order high pass network, we can write the transfer function. This is the transfer function for this simplified first order high pass network, and from this expression we can write lower 3 dB frequency, that is omega L is 1 by RC. On the next page, I'll explain a small signal equivalent circuit for common drain amplifier at low frequency band. This is all about a small signal equivalent circuit for common drain amplifier working at low frequency band. These two are high valued coupling capacitors, and this is the input voltage source. This is the internal resistance of input voltage source. This is the biasing resistor. Vi is the input voltage across bias resistor. This is the source resistor across which output is taken. This is load resistor. This is the output resistance of the device, and GM-VGS is voltage control current source. And after simplification, we get this diagram. This is a small signal equivalent circuit, and R0, RS are in parallel, and the source comes here and drain comes here. Since there are two coupling capacitors, they contribute frequency dependent factor in the expression of transfer function of overall voltage gain or current gain for the case of common drain amplifier working at low frequency band. That is why there are two lower 3 dB frequencies corresponding to CC1 and CC2. On the next page, I'll explain one method known as short circuit time constant method for the determination of one effective lower 3 dB frequency for common drain amplifier working at low frequency band. On the next pages, I'll also explain the effect of these two capacitors separately. For the determination of pole frequencies for common drain amplifier at low frequency band, we can also use S-domain analysis, which becomes tedious with the number of capacitors involved. I'll explain a new method known as short circuit time constant, which is also very useful when we are not sure about pole frequencies and relative other pole frequencies. This short circuit time constant method approximates any high pass network of higher order into first order network, where only one effective lower 3D frequency can be defined for quick analysis of the behavior of any amplifier at low frequency band. Let us start writing the transfer function of overall voltage gain for common drain amplifier with two poles. So this is the expression for transfer function with two poles, and it is showing high pass network characteristics. These are two pole frequencies corresponding to, this is corresponding to coupling capacitor CC1, this is for coupling capacitor CC2. At lower 3D frequency, the denominator should be equal to root 2, just opening, and considering this denominator is far greater than this numerator, and this imaginary term will be unity when denominator is equal to numerator, and this is a condition. And this is called effective lower 3D frequency, which is a sum of two pole frequencies corresponding to both coupling capacitors CC1 and CC2. In fact, the sum is equal to the sum of reciprocals of the time constant corresponding to these two capacitors. We can write this expression in terms of Hertz, that is effective lower 3D frequency in Hertz FL is 1 by 2 pi and sum of reciprocal of time constant corresponding to CC1 and CC2. There are two steps involved because there are two capacitors for the determination of time constant. In the very first step, we have to select one capacitor out of these two. Suppose I am selecting this one and will consider this capacitor as a short circuit, then I will find out the resistance seen by this capacitor CC1, or I will calculate Thevenin equivalent resistance across the terminals of this capacitor. Then I will write this expression of time constant corresponding to this capacitor. In the next step, second step, I will consider this capacitor and assume this capacitor as a short circuit. Then I will find out the resistance seen by this capacitor, or I will try to find out Thevenin equivalent resistance across the terminals of this capacitor. Then I will write this time constant. On the next pages, we will be determining time constant separately for this capacitor and this capacitor. Then we will write a full expression depicting effective lower 3D frequency for common drain amplifier at low frequency band. As per short circuit time constant method and step number 1, I am selecting this capacitor and considering this capacitor as a short circuit. Now I will determine the resistance seen by this capacitor, or I will determine Thevenin's equivalent resistance across the terminals of this capacitor CC1. For this, I have to use Thevenin theorem, and as per Thevenin theorem, I have to replace this capacitor by a test voltage and putting down input voltage source equal to 0 as a short circuit, and this will be open circuit. And in fact, this part of circuit will not be very useful here, so I am considering only this part. And considering this loop, we can write down the current flowing through this loop, that is IES Vx divided by total resistance Rs plus Rg. From this expression, we can write Thevenin equivalent resistance for CC1, and this is equal to RCC1, this is Vx by Ix, Vx by Ix, that is Rs plus Rg. And now you can write time constant for this capacitor CC1, that is RCC1, CC1, Rs plus Rg into CC1. On the next page, I will select this capacitor and consider this capacitor as a short circuit under step number 2. As per short circuit time constant method and step number 2, I am selecting this for the determination of resistance seen by this capacitor and will consider this capacitor as short circuit. Before the determination of resistance seen by this capacitor, let us define two resistances R0 and R. R is the total internal resistance of this voltage controlled current source, and R0 is the total output resistance of the amplifier looking at this plane towards the amplifier. So as per Thevenin theorem, replacing these 2 points with a test voltage and using this equation, VGS is Vi plus Vx, and when Vs is 0, then this Vi will be 0 and VGS will be Vx. Then this voltage control current source will be GM Vx. And from this loop, we can find the value of R, that is 1 by Gm, and R naught is the parallel combination of this 1 by Gm and R naught and Rs. In this way, we can write Thevenin equivalent resistance for CC2. It's very simple, and it is a serial combination of this as well as RL. So this is 1 by Gm, R naught, Rs in parallel combination plus RL. This is load resistor. Now we can write time constant for CC2. So this is a expression for time constant for CC2. Now we have calculated and determined the time constants for this capacitor and this capacitor. Now we are in a position to write complete expression for effective lower 3 dB frequency for common drain amplifier at low frequency band, just on the next page. So far we have determined time constant for both the coupling capacitor CC1 and CC2. Now we are in a position to write complete expression for effective lower 3 dB frequency for common drain amplifier at low frequency band. In fact, FL is equal to 1 by 2 pi sum of the reciprocal of the time constant corresponding to both the coupling capacitors. And RCC1 is the resistance seen by CC1, RC2 is the resistance seen by CC2. Substituting the value of RCC1, RCC2, so this is the complete expression for effective lower 3 dB frequency for common drain amplifier. So this was all about performance of common drain amplifier at low frequency band and the derivation of the expression for effective lower 3 dB frequency for common drain amplifier.